Thank you for being here. You will either very much regret it or won't regret it, but nowhere in the middle. So about small data optimization, specifically in the context of when the data is small enough to store inline. So consider the string type in Rust, where you have the pointer, the length, capacity, and it's always going to reference something outside. Likewise with borrowed strings. However, in that same space that you could be storing the pointer, the length, and capacity, or just a pointer or length, or in some cases just a pointer, you could actually be storing the string data directly there. So I'm going to be demonstrating how to do exactly that. So when would you want this? Some libraries, such as LLVM, have a small string type where you're able to parameterize the size, and this idea ended up catching on within the Rust community, and now there's actually many libraries to do this. There's smallvec, tinyvec, and so on and so forth. And the benefits that you get here are mostly found in programs such as parsers or anything that has to deal with like binary packets of data. And so I find that even beyond that, there's still benefits to be had with using this, because in general, I find that most strings that end up being used in most programs are small. And so if you can store them on the stack, that can be a lot more efficient than having to heap allocate it. So I'm going to demonstrate how to implement this using enums in 100% safe Rust. Oops. All right, so can you all see this well? All right, so I created a Rust project where I just have the package, the edition, the version, and I don't intend to publish this. And later on, I do intend to benchmark this. So I did create a simple file with the empty benchmark harness to run main. And so this is as simple as a package definition can get for this kind of thing. And to start off, let's actually define our enum for our public API. So let's just call it enum string verbatim. And well, we're gonna wanna store allocated strings. So let's make sure we have a case for that. Okay, so we're off to a good start. And this actually gives us a lot of great things for free. For example, enums are able to, they don't necessarily implement drop, but what they store implements drop, then it's kind of like a transitive drop. In the standard library, there's a function called std_mem needs drop. And so rather than check trait bounds against drop directly, instead you can use this function. So already, right from the start, we're going really well. We have heap allocated strings, basically just for free. So let's do our inline string. So as I mentioned, it's a byte buffer. And so let's just make it an array. What size would you all think this should be, out of curiosity? I heard 8. 16. 24. 23. 42. I like 42. It's not practical in computing, but it's practical in the universe. So 24 and 23 are actually kind of the numbers here that are good to work with. But let's just go with 24 in this instance. And so here we end up with, on all platforms, this is able to store inline at least 24 bytes. And in the case of in the case of 64-bit, this would be the same as if I just did std_mem size of string. However, now if I did that on 32-bit, it would actually be half the size of what it would be on 64-bit. So rather than 24-bit, it would be 12 bytes stored in line. And this is part of the trade-offs that you need to consider in this space because, well, maybe you do actually want smaller inline buffers, or maybe, well, actually 24 is actually a size that you get close to, or you're always staying underneath, regardless of platform. So it's very context dependent, and so what what libraries will do is that they'll provide a constant generic parameter for this, and you could just define it like that and determine the inline storage directly. However, for the purpose of this talk, I'm not going to be dealing with generics like that, so I'm just going to keep it as local constants. And for that matter, let's move this constant out into its own. Okay. So we've got our enum string, and we want to actually turn it into a string. So let's try to do exactly that. So first, what we would want to get is consider, well, we need two things. We need a pointer and we need a length. So let's start with getting the pointer. So if this is a pointer string, then we would end up having either, or we would be referencing the alloc case. And if it's inline, then it's directly there. And given that this is already an enum, we can just do matches and then check this ourselves, given that the Rust compiler is able to just understand this. And that's really nice. So if we wanted to do more manual stuff, it would make sense to have this isPointer method. However, for the sake of this, we can actually just do pattern matching and get away with that pretty well. So we've got our, sorry. Okay, so here we're going to either be referring to the allocation or the start of the inline buffer. And if we're going to be referencing the start of the inline buffer, well, we also need to store the length somewhere of the inline buffer. So generally what I advise here is the end is pretty good, because what happens in the generated logic is that you don't end up with offsets outside of having to dereference into the string. So it just ends up generating simpler code. And we want to convert this to a string, which is ultimately what the point of this wrapper is, right? So given that we already are working with the string with capital S, we can just call asStir and be done with it. Or we don't actually even need asStir. We can just use the string reference directly because it implements deref. And whereas with our inline representation, well, we've got our data at the start of the buffer, and then we've got our length at the end of the buffer. So here we don't actually even need to use this pointer method, or rather, it would be asPointer in the case of the naming convention. And because we have the Rust compiler to provide us with this powerful pattern matching, we can just directly create our string from the array as if it was kind of like a slice, although as you can see here, it ends up being a array reference. So at compile time, it's able to create subslices that aren't dynamically sized in a sense. So let's actually convert this to a string. So std_stir from UTF-8, and then we want std_slice from raw parts, and then data as pointer. Oops. Right, here we go. and then the length is actually currently a reference to a U8, and so what we would want is to dereference that U8 and then convert that to a U size. And then we can just unwrap our string. This is, all right, so this was, all right. So you do need unsafe for here. Or if I'm, let me look at my notes actually. Just trying to get it off of memory. Yeah, sorry, you don't, for whatever reason, I forgot that actually subslicing is a thing, because that's what being on stage does to you. So yeah, we can just directly ask it for the, right, we need to dereference the length. And so this is actually in fully safe code. My mind was on the second part of this, which will deal with unsafe. And so now we've implemented this type where it can either be stored inline or it can be stored as an allocated string. And in order to actually, for it to be useful, we need to actually have it be instantiable. So let's instantiate it by implementing from stir. And then we want to check if it's within the, if it's inlineable, then what we can do here is, actually, just to speed things up, let me pull up my all right, so the implementation for from stir ends up looking like this. Rather than having to do anything with allocating manually ourselves, in the alloc case, we can actually just call string from and then store it directly, whereas it's much more involved in the inline case. However, the code itself doesn't end up actually being that complicated in what's being generated. So here we're storing at the very end the length byte, and so we're converting from usize, and then given that it's within an inline size, it's of course never going to overflow 256, or at least in this case, given a constant being provided directly. If it was a generic constant, then that does become a concern, although, yeah, I guess 256 on the stack doesn't sound that strange when you can be buffering like 8 kilobytes at a time usually on the stack, although that wouldn't be usually strings. But in this case, this doesn't just apply to strings. This technique generalizes to any data. It's just simplest to understand in terms of strings, and hence why I'm explaining it this way. So after we've assigned the length, then we copy the data over, and when you copy the data, when you call copy from slice, both slices need to be the same length, and so we need to reference up to where we want the end of the data to be, and then we can just reference all of the bytes from the string. And then now that we've done that, we actually have our own buffer. What I did separately here was I had a wrapper type, but it would be effectively the same as if it was directly a byte buffer. So from here, what we can do actually is we can consider that, oh, sorry, I lost my train of thought. We can consider that because there's no unsafe, this, even though it is a bit tricky to read, we can actually test this fairly thoroughly, and because we're using unwraps, that ends up getting caught at runtime. We could then move to unsafe and do unchecked unwraps, and what we would then do to test it is use MIRI. So to get to that point, let me demonstrate how you would implement a slightly more efficient form of this without relying on enums. So we had our enum string, and just to have the implementation be complete for later benchmarking, let me copy this in. All right, line length. And then, all right, now this implementation is complete. And we can just, let's move it to a separate file. So, and then create a new lib.rs. So now that we know what the Rust compiler can do for us out of the box by default without trying very hard, let's go out of our way to manually manage the memory so that we can actually get the most performance possible. So to do that, we're gonna, in order to have manual control over the memory, we need to have a C representation for a struct, because that tells the Rust compiler, lay out these fields in the same order that they're declared in. And so the reason this ends up mattering is that where you end up storing the tagging could end up changing from underneath you, since normally the Rust compiler is able to reorder fields. And in this case, all the fields are basically the same as vec. They're all a single word, and in the case of a single word, I find that the Rust compiler doesn't actually end up reordering things. However, there is a flag to randomize layouts, so if you want to improve the testing of your code for things that are sensitive to this, where you forgot to put repc somewhere, then you can be able to catch those issues. And so how do we want to tag this string? Can I get some ideas from the audience?
Use the last 3 bits from the string allocation.
Use the last 3 bits of the string allocation. What do you mean?
From the pointer, the allocation is always going to be 8 aligned on 64-bit platform.
Okay, but does Rust guarantee this?
Technically, no. unless you do the allocations with the allocator API, then you can specify layout with the alignment you want. So
right.
you get more bits.
That is true. You can use the allocator API, although in this case, we're going to be using string, which uses vec, and pointers between vec and alloc, unfortunately, aren't compatible because there's room left open for future optimization. So, for example, one thing that they're considering is rather than have arc have the reference count be before the data, it could actually be trailing at the end of the data, and then what you can have is O of 1 conversion from string to arcster in that case, where, or I guess boxster to arcster without having to do any reallocation. So, well, no, I guess that wouldn't work in boxster. It would have to work in the string case with a reallocation. But because boxster does store exactly the amount of elements it has, you wouldn't have that spare space needed for that reference count. So this optimization wouldn't actually work for boxster. But back to the topic at hand. So yes, we could do pointer tagging. However, given that we're not in control of the allocation, that seems fraught with issues. Other suggestions in the back over there? Use a null. Okay.
I was thinking the most significant bits of the length are likely going to be 0. Yeah.
The most significant bits of the length are likely to be 0. Why is that?
Because it's a bit hard to make 4 gigabyte strings even on a 64-bit platform.
You know what's even harder and actually impossible is to make a string that is 1 size greater than I size max. And so that is actually what I'm going to take advantage of here. So Rust guarantees 2's complement arithmetic for U size, and thus U size and I size can be basically represented in terms of each other. And so if we took the top bit of the length field, then what we could do then is just check if the sign bit is set or not. So to tag this as a pointer, let's just say that we want the sign bit to be set. So let's just do usize bits minus 1 is equal to 1. All right, so now we know that this is a pointer, and this is complaining because, oh, wait. Wait. Parentheses after the length? All right, let me actually look at the code I have for this, sorry.
It's telling you that it can never be 1 because you're shifting, so you actually always have the highest.
Oh, wait. I'm thinking of
So
if it's
you shift the length to the right, or you just compare to 0.
Yeah, so I was alluding, so actually I was gonna get to that point. So what I can do in this case is just self.len as I size is less than 0. That's another way of checking the sign bit. Okay, so now we have a constant for the sign bit, and what I was actually trying to do before was self.len and sign bit is equal to 1, right? Or is it? Oh, right.
It's not 0 because the bit is not 1. The sign bit can never be 1, so you can never get 1 by doing a bitwise append.
No, but the sign bit can be 1 because it's usize that I'm dealing with.
No, your sign bit is a constant, and it's always only, it's always bat. Saying it's not 0.
Oh, not 0. Oh, right. Okay, sorry. Thank you for explaining that like 500 times in the same way, and then until I finally got it. Because this is how live coding goes. Thank you for being patient. So, yeah. Essentially, these two comparisons end up being the same, and to guarantee that, we can actually generate the assembly code that would be used for this. So I have a little script that helps me generate the assembly. So here's the ARM code for this, and as we can see, what it's actually end up doing is it does a logical shift right. So essentially, yes, it is taking the sign bit over rather than doing an AND. And this also should generate the same code. And yes, so the Rust compiler, or maybe more so LLVM, is smart enough to recognize what ends up being the sign bit. And so we can actually take, we can do a lot of interesting things with this. So for example, not only do we have logical shifts, we also have arithmetic shifts, which means that we could take the sign bit and create a mask of all 1s or all 0s, and that can be used to create branch-free code, which allows for more throughput. So continuing on, and because I am behind, let me cheat a bit more and copy and paste. And of course, the only difference is that it's not the 2. So for the actual length, oh, and yes, this was, I wanted to make a point with little endian as well. So let me add that so I can remember. So in order to get the actual length of this, what we can do is we can remove the sign bit, and then if it's a pointer representation, the length is already going to be the full word, so we can use it as is. However, if it's inline, it's going to be in the last, or in the most significant byte. And so, which in little endian is the last byte. So, and hence the reason why we have the 2 little endian conversion. This essentially gives us have the same code basically work with a little extra cost on big endian machines. However, byte swap should be pretty fast. And when was the last time any of you have used a big endian machine? I'm actually curious. 1997, 15 years ago? Yeah, exactly. So, embedded, okay. Recently? 2 years ago, okay. All right, well, it is actually worth considering, but I don't think it's worth necessarily hyper optimizing for. And so that's why I think the trade-off of just doing a byte swap is fine. And we're getting a warning here because Clippy's insisting that we should have an isEmpty check. I'm just going to allow, actually, let me just do the isEmpty. Because if I have time, I want to show the benchmark for that, which I think I should have time. All right. Okay, so now that we've done our tagging, or at least we know where our tagging is happening, there's a few things that we could actually improve here. So the generated code here for length actually ends up, in the case of, so in the case of ARM here, we actually do get branch-free code, even though we do have a branch here. And so you're essentially at the whim of the compiler on whether you're going to have branching or not. In this case, the x86 code, for the case of length, also has branch-free code. However, turns out that even if the components have branch-free code, the ultimate result may not. And so let's actually convert this to a string. Now that we actually need to get the pointer first. So as pointer, okay, so here simply we just, if it is a pointer representation, we read the field as is, and we're allowed to do that because ideally if it was instantiated correctly, then it has pointer provenance and all the magical things you need to be sound, because it is a real pointer, not an integer pretending to be a pointer. Watch out for those. They sneak up on you. So now that we are able to convert this to a pointer, we can also convert this to a string. So let's do exactly that. And I'm going, since we're already in unsafe land, let's go more unsafe. And we're always coming from a proper string slice. Why check UTF-8 every time? Oops. All right. So now that we have our pointer and we have our length, we can actually convert it over. And with what I was alluding to before, the sum of the parts may not actually be branch free, even though the individual parts themselves may be. So, and actually it seems that it also has affected this code, which is interesting. So did that actually change because I'm calling it? Oh no, that did have a branch, never mind. Or am I hallucinating? There wasn't a branch there before, was? Or, oh wait, no, I hadn't gone on to that code. Okay, wait. Okay, I remember, yeah. So what I'm ultimately gonna get to. So what's happening here is, yes, we have a branch for as pointer, but sometimes the optimizer is able to be really weird with stuff. So let's consider over here where we have this conditional shift. If we wanted to make it unconditional and we wanted to always shift, one of the ways we can have a value to shift by is we can do if it's going to be inline, we have a shift. If it's not, then we don't. And so given that Booleans are 0 or 1, we can multiply by a Boolean converted to an integer and essentially make it be the value itself or not the value. Do I need to wrap this further? No, what happened here? Oh, right. Okay. So now, if we shift this over, and we go back to our as stir, well, that's for the arm, we just changed the code for length, and it removed the branch for getting the pointer. Are there any compiler devs in here who could explain why? Well, it's always, given it's within the same crate, I mean, I could, if I slap inline on everything, it also ends up with the same code. But it's doing the same amount of inlining either way, I think. And actually, if I slap inline on the previous implementation outside of the as-stir, I actually do end up getting the same code. So I don't, it didn't, so, and if I did inline never, I'll just get function calls. But anyway, so now we're actually kind of at a more ideal situation with this code. Let's actually be able to convert it from stir, and I'm going to cheat on that as well. Yes. So the C struct is composed of the, starting with the pointer, the capacity, and then the length. And then what I'm essentially doing is I'm storing both the pointer length and the inline length inside the same word, but instead of, in order to also use all the bytes up to and through the length, the inline length is stored as the last byte. Does that clarify things?
So you're using, when you're having an inline string, you're using those 24 bytes of those three words.
Yeah, so I can store up to 23 bytes here because the last byte is being used as the length.
And you've got an implicit union, essentially.
Yes, exactly. I've created my own union, yes, by reinterpreting the bytes as through pointer. Okay, so the, yeah. And then I can cover the padding if I have time, but I don't think I will. And the, yeah, so. Oh, right, because of course it imports the wrong size of and imports the intrinsic. All right, so this is how we would actually instantiate for the allocated version of the inline, or sorry, of this inlineable string. I did find that and I need to report this, there's a bug where if I instead were to do string from S, MIRI complains because I think pointers are being gotten through the wrong way. And so that's why partially why I mentioned that the integers might sneak up on you, because even the standard library is not safe, or safe from this. It's generally actually very safe. So we now have, we're now able to instantiate our strings. We're able to dereference them. Let's actually, well, we haven't fully instantiated them yet because that's a to-do, and it's not the, I initially planned more, but unfortunately my hostel had me late, so such is life. But let me just explain this code then, or rather, where's the, here we go, sorry. All right. So here we know that the length is going to be at the end, and so we can do pattern matching to grab that. We can then assign it through the reference, and then we cast to U8 because we cast to U8 because it's expected to be a byte, and it's never going to overflow because inline size is only 24, pretty far from 256, I would say. So, and then we can do a copy from slice. We could also, so actually since the optimizer is able to see this check here, it ends up eliding this bounce check. So even though we're writing a lot of unsafe to make this happen, you don't actually have to fully commit to unsafe to make things optimal. The compiler can be fairly smart about some things. And so now we actually have our full implementation. Let's benchmark this. So I had created a benchmarking library called Devon, if some of you may be familiar with it. If I have Wi-Fi, it will work this way. All right, perfect. And the way you set up, the way you just call into it is just run main, and then it will just run all the benchmarks that you registered. So let's actually benchmark this. So let's start with benchmarking from string, because that's going to be what's most benefited from inline optimization, since it won't be allocating. So we can provide a generic type, and we can provide, right now, sizes or inputs are through const generics. And we provide a bencher. And we want to actually register this function. So we want to have this be over string. We want this to be over, let's just say stir, because stir does implement from stir. So where T is from static stir. And then we also want to implement this for our own strings. So let me pull in the enum string. And why is this complaining now? Oh, right, I need to provide constants. And then all right, those are good sizes. And then it was tag string. All right, so we've set up this benchmark as far as from what Devon can see, and we need to actually generate strings that we're going to be constructing from. So let's give ourselves a nice buffer to work with. So and then take n of these, collect them, and then benchmark over creating these strings. And then this, oh right, it needs to be static. So this wasn't the way I had. Let s static stir equals.
Or you can just change the from bound.
Sorry?
Change the from bound. It doesn't need to be static.
Unfortunately, it does in this case. It's a limitation. Yeah, I can leak it. That's true. Thank you. So All right, we are now leaking. Great advice. Uh, there we go. And let's also black box this to make sure that the optimizer is not able to do anything. All right, so we've now written our benchmark, and let's actually run it. So let's and just so then we see that there's actually progress. Let me not do quiet mode. All right, so we've now checked from stir across these implementations, and we see that the fastest implementation by far is stir itself because it's almost effectively a no-op. And then second fastest to that is the tagged representation for inline strings in very close competition with enum strings. So even though we did a lot of extra work to kind of micro-optimize, in this specific benchmark, it didn't really change that much. However, in other cases, such as considering the fact that you need 4 words for the enum string because you have one tagging byte that needs its own whole word, you're wasting a lot of space. So anyway, in conclusion, the enum string has a lot of nice properties, but at the same time, we could do better, and we've seen what better can look like. However, we also need to measure and see if better gets us the results that are actually better, and it's not just going to be a maintenance nightmare. So the enum case, much simpler to understand, easier to maintain, 100% safe, much less likely to have bugs and security vulnerabilities, although it will use the extra space because it's using 4 words. So it's not going to use the 3 words that string can. And the compiler will try to do things well for you, but you're very much at the mercy of it with layout is concerned here. Whereas the tagged version, we're able to, in the same exact space as string, we're able to store inline storage. And not only that, I didn't get to demonstrate it here, but we could actually change the, in this case, it wouldn't be changing the pointer to non-null. Instead, it would be having a niche of the max U8 for the length byte. And in my string library, I end up doing this. So there's a lot of nice benefits. However, we end up at the same time, it is a bit of a maintenance nightmare, and the performance may not be what we wanted it to be. And as a result, we should be actually measuring this. So hopefully you all got a lot from this, and thank you so much for coming.
Okay, we don't have time for questions, but you can meet Nikolai at the coffee break maybe and ask him here. So I'll send you at the coffee break. Thank you, Nikolai. Nikolai Vazquez.
Yeah, and just to call out a few things. So I'm soon publishing a string library that implements the second unsafe version because there is actually benefits to doing that. It's just in this case, the from stir benchmark ends up being basically equivalent, regardless of the 2 implementations. Please try out Divan. I'm very excited to see what people are doing with it. Also, I'm working with Predrag Grevsky to make the query engine trust fall much better. It's what powers cargo semper checks, and I think we can make a lot of interesting tooling with that. So Yeah, thank you so much, and hopefully that wasn't too cursed for you.
Nikolai Vazquez.